Welcome back. Could you please confirm my slide and audio is reachable to all online students?
Yes,
That's great. Okay. We had a small discussion here with the textbooks and examination point of view. That's why my recapping of the class has delayed little. So I had shared the soft copy of the textbooks to the students who are here. I given the PDF version, so you can also get from them for your learning. And we continue with the discussion of today's class. So in order to make your dynamic modeling of your synchronous machine, this is the most simplified equation where you have to have the information of your resistance of your armature, reactance of your direct axis and indirect axis. Then you can easily calculate or control the parameters of your active power and reactive power. Then how to make a synchronous machine with a damper winding? Anyone remember what is damper winding? What? Okay. So usually, if you look at the DC machine, we have a armature reaction. So what is a armature reaction? Due to the continuous rotation of your rotating part, which is armature, and you have a fixed poles, the poles will not rotate. Only the armature will be rotating. So you get a neutral axis when the pole of your rotating armature and the fixed pole are exactly in same sequence or vertical. For example, the most easy is to say the exactly vertically coincide. But due to the small deviation of the induced EMF within your armature, it also generates some voltage, induced voltage, which is opposite to the direction of the main field. So you have a main field, say, from right to left, but the field from your armature is from left to right. They are in opposite. So this resultant will make your armature, or I say the brushes in your armature, to shift from neutral axis. So neutral axis, you'll have zero flux, zero current flow. That is the principle of the electric DC machine. So this neutral axis will be shifted little. Because of that, you create also sparks. When you have a DC machine, you go to the lab, you are finding spark in your brushes. The reason is armature reaction. First case. Second part, maybe you can have damages in your brushes, etc. Then you create sparks. These are the major reason why you get sparks in your electric. Same, it will happen for your synchronous machine. Why? Synchronous machine is like a DC machine. You run your synchronous machine at synchronous speed, whereas in induction machine is not happen. We have damper winding in induction machine, but for huge machines, we use high speed machines. We never use damper winding effectively in your induction machine because armature reaction is very limited, very limited, near to zero. Yes, but in case of synchronous machine, we have armature reaction because you apply a DC excitation to your field winding. So his behavior is like a DC machine. In order to overcome that, we use a damper winding. We put a winding. We create a magnetic field which is opposite to the field which is created from your armature. Then I neutralize it. So in electrical terminology, if you have some component, current and voltage, you want to kill it, you provide an opposite current, opposite polarity current. Then you neutralize, I'm right. For that purpose, we use a damper winding. I'm not going inside. So if you are modeling your synchronous machine in dynamic way, you have to consider this. That's very important. So if you consider also the damper winding, then how to calculate your direct axis flux linkage is given by delta D. Quadrature axis delta Q is given here. And for the zero sequence component is given here. And this is for your field excitation. Then comes how to calculate for your damper winding. So now damper winding is also energized. It creates flux linkages. So in order to calculate your flux linkages in your damper winding, this is the equation. Because of the damper winding, we can also calculate d-axis, and with respect to the G, these are the various flux linkages you have to calculate. All the equations are given, final equations are given. You can directly calculate for your dynamic model. So your ambition is like you should familiarize only with the resultants to make your models. Can I go to the next one? Then we are going to look at the equivalent circuit of your generator. So this is all available in your basics of your bachelor degree, but still I go a little inside to show you because you have different reactants due to the field G and AD. This is due to the damper winding. This is a model, but you want to make your synchronous machine equivalent circuit very simple. You make all these to be negligible, then you will have only your quadrature axis reactance. You don't want to have your direct axis. So if you want to make a simplified model of your synchronous machine, you are going to have a reactance, which is in your armature on the armature side in series with your quadrature reactor. That's it. How to do that? You have the formula, you see here. So you get the parallel values all combined together, you find the equal. It's a very simplified model of your synchronous machine to make it more easy for the analysis with the equations. Can I go to the next one? Now, how to make the final part of today's presentation is very important. Modeling of synchronous machines using swing equation. Swing is very important because you know already the output power of your synchronous machine is V divided by X into sine delta. I'm not talking in the point of power system. I'm talking in general. You have a delta, which is an angle varies from 0 to 90 degree to 180 degree. At 90, you get the maximum power because your formula is also represented as V by X into sine theta. Sine theta is the maximum parameter for your output power or torque or active power. So theta equal to 90 means sine theta is 1. If you put sine 0, your output is 0. So in order to make the swing equation, we are controlling the power of your armature. We have to consider the power developed from your synchronous machine, which is PA, is directly proportional or equal to M into d square delta by dt square. So you need to find the second derivative of your torque angle. This is called your swing equation. Now we are going to make this swing equation more linearized or simplified form. For this, we are going to consider this part M into d square delta by dt square, which is nothing but the mechanical power minus electrical power. So you know what is the output? The input is a mechanical power, output is an electrical power. So which is nothing but Pm minus Pe. What is J omega? J omega is nothing but the M. How to calculate this M? Is nothing but J omega, angular frequency. It's clear to you? With J is the moment of inertia. It's clear to you how to use the, I didn't go for the derivation. If you want to learn the derivation, follow the textbook. There is a procedure. You can apply the procedure. You can calculate how to know the dynamics. But for the application part, this is enough. Then I say my swing equation is also expressed as M into d square delta t divided by dt square, which is nothing but Pm, my mechanical power, minus how to calculate the electrical power, EV divided by X into sine delta. Now you control your delta, you control your swing equation directly. Where P equal to what is your is EV divided by X into sine delta. So this part is only your electrical power. For using the swing equation, you must know also your mechanical power. It's clear to you? Your mechanical power is nothing but torque into speed. I'm right. The output power is very simple if you know the basics of electrical machines. So for developing all these equations, there are some assumptions we need to follow. What are the assumptions? Synchronous machine rotor speed must be synchronous speed. It means that your rotor rotated at rated speed, synchronous speed, 120 F by P is the first assumption. Second assumption is that your frictional and windage losses are neglected. So we assume in order to make a swing equation of your synchronous machine more compact form, we take this assumption. Third one is the mechanical shaft power is smooth. So there is no any huge deviation in the mechanical shaft power or oscillations or vibration in your shaft. It's absolutely free of mechanical losses. These three we consider, we find these equations. So if you want to model a swing equation of a synchronous machine, these three are the assumptions based on which we derived m into d square delta by dt square equal to pm minus ev divided by x into sine delta. It's clear to you? By this model, you can easily further model your synchronous machine. It's clear to you? Then I'm going now to blocks, how to develop these machines into a block diagram. So modeling of your speed governing system has two types. You can go for a mechanical hydraulic control, electric hydraulic control, because the electrical power generation from your hydropower plant has two parts, mechanical parts and mechanical electrical parts. Mechanical parts is your turbine, rotation, the machine design, everything with the mechanical. Output is your electrical. So we have two parts, how we can make it. For example, this is a system, you can have a look. I have a speed relay, which controls the speed. The input is my reference. So I set here 1500 RPM, 500 RPM, 200 RPM, 2 RPM, whatever the speed I want. Then the feedback is the actual speed from the system. So this is my speed sensor, speed governor system. I have the feedback, which is given to a hydraulic servo motors. So what is the meaning of servo system? Servo system is like any perturbation, any disturbance is given, the system follows the input. It neglects all the, I'm talking not too much based on control. I'm just talking like a generalized terminology. So why we go for servo system? Servo system follows exactly the input and produces the output, neglecting all the disturbance. Then it is given to a governor controlled wall, which is the wall of your hydropower plant, and you get the position. So this is the functional block diagram of your speed governing system. So how to make a block diagram or representation to make a developments of the model for your speed governing system? This is a simplified model. Can I go to the next one? Can I go? Okay, now in detail. So already I given you some examples of MATLAB, how to model the complete one area network to an area. Already I given you also how to make speed governing system, load models. If you would have seen the simulation models. Also I given you the how to make a turbine and wind modeling in a simplified first order system. So now this is a model how we can make it. So you have an input SR, which is your calculator from your speed. We already seen this in your previous slides. Please have a look. So the feedback is taken from the speed, and there is a speed governor, which is a gain constant. Then it is given here. So you find the error. The error is compared with the feedback from your speed relay. So this is a loop 1 divided by S, which is the integrator. We put an integrator here. So we got an input, then we find the integrator. From the integrator, we given to a CAM model, which is a linearized function. So in this linearized function, I want to start my speed from 0 to maximum. You see, very smooth. So here I create that one from this system. Then I have a servo motor, which is my synchronous machine. This output is given, and since what is the position, the feedback is the position of my machine. Then again, I have an integrator, which is given by 1 divided by Sm, time constant of the machine. Then I have a limiter. What is this limiter? This integrator is a addition of time. I'm right. You know the meaning of an integration, addition with respect to the time periodically. So you have the limits of currents and voltage. This integrator can get saturated and it can go exceed the limited value. In order to fix that limit, for example, I have a machine, I know the currents, 10 ampere, then I can fix the limit, maximum goes to plus 10 ampere, minimum goes to minus 10 ampere. This is the purpose of the limiter. The limiter helps you to fix within the limits. and avoid saturation of your machine. If it goes beyond the rated current, what happened? You damage the machine, I'm right? You need a limited controlled system. So that's why we fix the limiters with the limit. For example, if you want to fix for the voltage, you fix the maximum voltage here and minimum voltage here. You can fix based on the calculations. Then again, it is integrated. Then we put the position. So here we have the speed. Based on the speed, here we are converting into the position of your rotor. Again, we put the position of the rotor as a limiter. What could be the maximum limit of your position? 0 to 360 degree. It's clear. You fix the position. Then you create the wall. This is the model for your wall. So from the position, you get a wall. It starts is linearly increases. You can see the model. So this is the model which makes a non-linear representation with a limiter. Then how to make a more simplified model of this real dynamic model? You can have a look here. SR, which is your set value of your speed. Then you get a feedback of your speed from the real machine, from the rotor, with a gain, which is going to be the governor constant. Then the error is given to the 1 divided by S plus tau SR. You know how to calculate tau SR. See my previous slides and current slides. You know how to calculate it. And the error is compared with the actual CV of your machine. Then the error is given to 1 divided by tau SM, which is the time constant of the machine. Then we fix a limiter for open and close. See, when I want to close, this value have to be. If I want to open, I go here. Then this is integrated because this is the limits for opening and close. When I integrate, I get the value for my wall. So wall goes to the maximum, wall goes to the minimum. I can able to control my hydraulic turbine. So if I already given you this model, please look at my simulation models. Already this tau SR example is given to you to model this one. Then in this case is very important. These are the parameters you can't find in other textbooks, which gives you a clear vision how to calculate the value. If you want to calculate the value of your mechanical hydraulic system, that variable kg, how to fix this kg? It's like a 20 standard. How to fix your tau SR, which is a speed relay time constant. The value is 1.1 second. What is the value of your tau SM, which is the position servo time constant, which is given between 0.2 to 0.3 seconds is the maximum variation. Maximum you can go for 0.3 seconds, minimum is 0.2 seconds. How to fix the value of your servo rate limiter? You can see here, CV max for open and close. How to fix the value? If you fix 0.1 per unit per second, per value for C open. For CV close, again, it is going to be 1.0 maximum because it goes to the maximum, the close. So 1 per unit per second per watt. So you have the guidelines how to fix all this in MATLAB or to model the system in any software. Can I go to the next one? Now I'm going to move from the mechanical part to the electrical part. So first I finish the turbine model. I design the turbine model. I fix each values. I know how to design it in the software. And I finish my mechanical part. Now I'm moving to the electro-hydraulic control, second part, speed governing system. So in this case, please note for this system, kg equal to 20. The constant is tau SM, which is going to be 0.1 second. And kp equal to 3 if you are going to use a steam flow feedback, steam turbine. And if it's going to be 1 without steam flow. For hydraulic, it should be 1. For steam, it should be 3. So these are the guidelines. We have to use this. You can ask me how they find this value. Many trials, many testings with different machines tested in real time. They find all this. Otherwise, we can't able to design the system. So how to make the model? You can have a look. You have the speed reference. This is the speed controller. What is the speed controller will do? It will find the difference between the set speed. This I will set 1500. And this is the feedbacks of the speed. This is the speed transducer, which will sense your armature or rotor of your machine. What is the speed it is actually running? And this error will be given to the speed controller. From the speed controller, the output will be given to the load controller. In the load controller, this is the reference, and this is the load reference what you give. It will be compared and given to the pressure or position control. If it is going to be a steam, it's a pressure. If it is going to be um, hydroturbine, based on the position control. Then it goes to hydraulic servo motor. Then it is given to the governor controlled valve. This is a valve where we open and close of your hydraulic power tank with a non-linear feedback. So this system is a non-linear. That's why we give a feedback and it is controlled. So this is the complete closed loop system, how we are controlling our electro hydraulic mechanism of your speed governing system. Then this is a generalized diagram, but how to bring it into a real software? So this is the model. How to bring into the software? We have a gate servo limiters. CV open is going to be 0.1 per unit per second per valve. And for the CV close is going to be 0.1 second per unit per unit per second per valve. This is both the value is the 0.1 we fix. Now this is the complete block diagram. So this is my input speed. Look at here, input speed. This is the speed feedback. Then I have a KP, which is a proportional gain constant, a gain. From the gain, I calculated what is the reference I given here. Then the feedback is taken from the machine. You can see MHP is calculated, which is having a feedback KP -1. So this is called feedback gain. So with the feedback gain, I find the minus, I find the error. Again, I given to the servo mechanism. So here I have the input. From the valve output position, I take it here as a feedback. Then I integrate by using time constant tau sm. You know how to fix the value. You can see here. Okay, everything is given explicitly to make the model. Then I fix the valve opening and close. We already seen how to fix it. Then I integrate this one in order to find the position. Now I get the position. I know how to fix the value of C max and V minim. Then I make it a closed loop here. So this is the complete model we have seen in the beginning. Mechanical part, hydro parts in the mechanical speed governance system. Now it's an electro-hydraulic part, electrical parts of the system. So when you combine both together, it's a complete power module of your hydropower plant. Can I go to the next slide? Then how to make it a combined model is a generalized model for a speed governing system. So for that, it's very important. All these time constant values, you need to have the guidelines. So the guidelines for your mechanical hydraulic system is tau1, which is going to be 0.1 to 0.3 seconds. Tau2 equal to 0, tau3 equal to 0.1 second. For an hydraulic electro-hydraulic system, you have tau1 equal to tau2 and tau3 equal to 0.025 to 0.15 seconds. So these constants, you have to have the guidelines. So I have this value. I fix with my system to understand the modules. With these values, we can able to make a generalized speed governing turbine module. For example, this is the forward path. From here, you calculate what is the value for your output power. So this is the output power I fix. I want the power. And this is the feedback I got from the PVG. If you remember here in the first slide, I showed you hydraulic the models, you get the idea from a PVG. So PVG is a hydraulic turbine with a speed governor. So same parameters we are feeding now here. This point. Then we get this feedback compared with the P naught, which is the output power what I required, which is integrated by an integrator, which is 1 by S, which is the tau3. You know the value of tau3, 0.1 seconds. And we fix the position. I mean, we fix the limits by using a limiter. What is the minimum down value, which is what is the maximum up value. Then again, it is integrated to find the position output of your valve. Again, we put a limiter here to control because integrator will get saturated and provide you exceed the limit. In order to avoid that, you put a maximum value and minimum value of your position. So you fix what you want the position output here. of the required power. So whatever the power you want, you fix the output position first and you get the value at PG. From here, you have to feed to your module here. If you want a ideal hydraulic, give the input here. If you want non-ideal model, feed it here. So now another important thing, how to fix the limits. So we have seen the limits here, limiters. So please note the rate limiters are normally 0.1 per unit per second. To fix these values of the limiter, we take a 0.1 per unit per second. And what is the value of your constant K, which is 100% steady state error. So SR is, you know, what is the steady, how you fix. I want the steady state error. For example, I want the wall to be open with a percentage error of 1%. I can calculate 1% of it. If I fix 2%, it's up to you, to your accuracy, you design with the percentage. It's clear to you? Can I go to the next one? Yes. Yeah. 1 over tau 3. Yes, is yes. But yeah, is an integrator time constant. Yes, you need to have yes. Yes, exactly. Obviously, yes. Yes. It's a time constant of your integrator. Usually when you put in your control blocks, you don't want to mention yes, because it's self-understand it's an integrator. But here you don't have any gain of time constant. There is no time constant. Time constant is 1. It's clear to you? So it's not specifically you have to mention here yes, but it's perfect if you put yes, yes, correct. You are correct. It's clear. So here, if you look at the time constant is 1. Then we are going little inside the speed governing system. Step by step, we are making the complete block diagram. So here I'm going to have a combining between the mechanical, hydraulic control, complete governing system. So you can have a look here. Speed governor reference is given. And this is the speed governor feedback from your machine, which is a hydraulic machine. Then you find the speed governor position. These two are given to the pivot valve and servo motor as an input. And these are two feedback, one from the distributed and gate server of your motor through a dashpot and without dashpot. What is the purpose of this one? Current position and previous position. So this will give you a position predefined before. And this is the current position. So you are calculating something an instant before and later. It's clear to you? The present value and previous value in order to make your system more precise. So that is given to your pivot valve and servo motor. On another side, we have a distributor valve and gate server. This output is given to a governor controlled gate and you control the gate position. This is the general mechanism for anybody to understand, but we are a power engineer. We need to model that. How to model? You are SR and your feedback is omega. You give to this differential amplifier. Then this is compared as a reference. You get the feedback from your transient droop compensation. You can see here you are getting from your position. So position is given to a feedback where you have a transient droop compensation. Again, it is taken the same position with permanent droop compensation. So you have the current value and what is the deviation. Both you calculate and you add it up and given as a feedback. Why we are doing this? In order to get the exact position, valve opening, what we decide. It's a compensation network. This is called compensators in power control system. Then this is given to a pivot valve and servo motor. Have a look how to model this one is nothing but 1 divided by S plus S1 plus S tau P. So first order filter. So first order system. Then this is integrated again 1 by tau G. So here it should be yes, it's not required. Usually when you have a gain with a limiter, obviously 1 by it's presumed integrated. It's clear to you? So if you want more precise, you can put yes, it's not a problem. Then here, what is the difference? This integrator has a 1 time constant. its time constant is 1. It doesn't have any other value. So again, you integrate with the gain. So it's a gain, you understand? This gain is combined together, integration is done. So it's the integrator. So don't with the gain tau g. Then you put a limiter in order to fix the value. It should not exceed the minimum and the maximum value, because integration, as I said, is a summation with respect to the time. You can exceed the value. In order to limit, we use limiter. If you look at my simulation block, I already used it. Then again, you put a position limiter in order to control the position, and given to a nonlinear function, you get C. So if you look at directly this side, you will confuse. Systematically, you have to follow all my slides to understand this modeling from the beginning. Can I go to the next one? Now we need to know what are the typical value used in these blocks, time constants. So for example, there is a tabulation value. Usually the typical value of your tau r and delta are computed as tau r equal to 5 times tau w. So this is the guidelines we use to design this one. And we are going to calculate different parameters. Tau r, tau g. So this is due to the governor. This is due to the position. This is due to the torque angle. And we have delta. So all these parameters, how we are taking a typical value, 5, 0.2, 0.04, 0.3, and 0.05. These are the typical values we use. Now to fix the limits are given here. What is the minimum and maximum? And how to calculate a delta? Delta is given by 2.5 tau w by 2h. So these are the formulas we apply for calculating each values of the parameters of your time constants of your block diagram. It's clear to you? And where tau w is the water starting time, and you know already what is h is a turbine generator inertia constant. So if you follow these guidelines, you can easily model the system in your software. Can I go to the next one? Now we are going to look at the generalized model of your speed governing system of the turbine. So I have a change in speed. The change in speed is given to the combined model of your complete hydraulic turbine, which is given by this block. Then I find the small change in the position, which is compared with the reference value. Then I put a limiter to limit the position between minimum and maximum. I get the value of PGV. How to find all these constants? That's very important. In order to calculate delta 1 and delta 3, which is equal, you have to find the value delta B divided by 2 plus or minus root of tau B square divided by 2 minus tau A. How to calculate K? 1 divided by sigma. Usually we take tau 2 equal to 0. These are the assumptions. You have to use the formula to calculate the absolute value of your power plant for the hydraulic turbine speed governing system, where P naught is the initial power, where PGV already we seen, which is the output of your governor, and it is expressed in per unit. Can I go to the next model? Next slide. Modeling with the limiters, that's very important. How to, we have seen many limiters. There are some guidelines to fix these limiters. So in order to make a wind up limiter, what is called wind up? So this widely, I don't go very inside to make you more complex. Usually the integrator will get saturated, particularly working with electrical machines. These wind-ups can cause saturation of your magnets in closed loop control system. In order to avoid that, we use a terminology called anti-wind-up action. So this is called a wind-up limiter. So in order to avoid saturation, we use a anti-wind-up action. For that, how to model? You have any system of your feedback of your integrator. You take it, given to a gain module, and you fix a limit L and H. Then you make within the controller, within the integrator, you fix these values. So for example, it can be any system of first order 1 divided by tau s, 1 plus tau s. Then you find the differentiation of dy by dt with respect to the output to the time. You get u minus y divided by tau. You fix the value. How to fix the value L and H? L must be less than or equal to y, and y must be less than or equal to h. This is the formula we use to fix the limiter of L and H to get the output Z, the desired output Z. For example, if your y is greater than h, the Z is going to be H. If Y is less than L, your Z is going to be L. So this is the way we fix the limiter required outputs. Can I go to the next one? Non-wind up limiters is very important. How to fix the non-wind up limiters? So for this, we take a equation yf is equal to u minus y. So u is your input, y is your output, and tau is the time constant. And this is a simplified model. So you have the u input, you have the model, you get the output which is required of Z. How to fix L and H? How to fix your upper limit and lower limit? For this, for example, if you take y equal to H and f is greater than 0, and y equal to L and f is less than 0, please use this f as capital. Both the cases is the same. Then you find dy by dt, which is going to be 0, because if you differentiate the constant, always 0. Differentiation of the constant is 0. Otherwise, dy by dt equal to f. Then I can fix L must be less than or equal to y must be less than or equal to h. So this is the limit we use for non-wind up limiters, when you're not having any anti-wind up action required in your limiters. Usually we don't prefer this one. We always prefer, for having a effective integration, we always use wind up limiters. It's clear to you? Then I want to make a complete model of my excitation system. This is the last part of today's discussion, because we have excitation also in your synchronous machine. So we finished mechanical part of your turbine, speed governing system. Then we move to hydraulic electroconversion part of your electrical system. Then we combined all together. There we also have excitation. Who will take care of excitation? So we have some standards. Here it's shown a IEEE type 1 excitation system. And this is the model which includes the excitation. You can have a look. So this is going to be the first block where 1 divided by S plus tau R. Already you know the meaning of tau R. I give the feedback, which is the VT output voltage. Then from here, I compare with the reference. So this is my reference signal of the excitations, and which is compared with the source signal. From this value plus minus, I get a reference value, which is compared with the actual value of my excitation voltage. You can have a look. And this is a feedback compensation network, which is calculated by S into KF divided by 1 plus S into tau F. Later, I will explain you all the terms, what is required. First, look at the control system, which is compared with the actual value. We find the error voltage, which is given to another compensation network, series compensation network, Ka divided by S plus tau SA. If you have this is called series compensation. This is feedback compensation. Then we fix the limiter for the maximum voltage and minimum voltage. And this is compared with the feedback of your actual value of your excitation voltage, which is given by F into ED. Then you calculate what is SC. You compare here, you given to your field excitation model. Then you make the system completely close operation. So what is EFD? EFD is the exciter output voltage. The terminology is very important. What is KA, which is a regulator gain? What is KE? Exciter constant related to the self-excited system. What is tau A? Regulator amplifier time constant. What is tau F? Regulator stabilizing circuit time constant. What is tau R? Regulator input filter time constant. What is VT? Terminal voltage, or I say it's a voltage required for the regulation. What is KG? Gain of the generator. What is IFD, which is a generator field current? What is IR? Generator feed terminal current. What is KF? Exciter saturation function. What is tau E? Exciter time constant. What is VR? Regulator output voltage. What is tau G? Time constant of your generator rotor field, rotating part. So this for you, how to learn, look at the block diagram, understand the variables. You need to find by calculation each variables and feed to the system and test it. So overall, I can say the transfer function of your synchronous generator in simple terminology. This is the model Kg divided by 1 plus S into tau G. You can see here, this is your simplified model of your generator. transfer function. What is kg? Kg is the gain of the generator. Tau g is the time constant of your rotor field. So if you look at the overall transfer function, it depends only on your gain of the generator and the time constant of your rotor field. This type of excitation is called type 1. We have type 2, type 3, etc. Some examples are given in the textbook also. You can have a look. But for me, one is enough because to understand how to do. But if you Google with IEEE, you can go to the website. There are different excitation model. How to improve the excitation of your synchronous machine. There are different IEEE standards. I given you one example. If you want to test, you make this model, insert all the time constant values, and you can test. Finally, today's presentation, I conclude. It looks more vague because it's equations, but in the matrix form. Why we do this modeling? The advantage is modern power system is controlled by modern control theory. For this, all become very standard forms, and you should be able to do with fast acting computers. So today's computers are super fast, and if you have equations, it can be processed in a few seconds of time or microseconds. For this, the most appropriate approach is called state space variable model. Today, whatever we discussed in the matrix form are called state space variables. So if you have a state space variable as a matrix in A, B, and J, it is well organized, very easy to synthesize solving this equation by using computers. And for example, if you look at a large power system, we are discussing only for one generator, one hydropower plant generation. If you have n number, these models helps you to determine in terms of a matrix. You can have a n cross n matrix for your A matrix, B matrix, column wise. Then you can easily calculate all the parameter in one equations. The complete power plant of your Norwegian region can be produced in one matrix with n cross n size for A, B, and C. And we fix symmetrical matrix based on the parameter. If it is going to be a voltage or current, if it's a current is a column matrix. If it is a voltage, also a column matrix. But the gain parameters, we put it in n cross n rows. So for these reasons, we make state space models, and we also follow IEEE guidelines standards. If you are going to use a DC excitation or AC excitation, you can refer the textbooks. There are many examples. If you want to make yourself familiarize, you can refer the textbook. So with this, I finished today's presentation. We can have a break for 10 minutes. Is okay, 10-15 minutes. Then, or if you want to make your lunch, how much? 15 minutes, 20 minutes? Okay, 15 minutes. And we can take 20 minutes. It's not a problem. We can meet maybe at 11:50. Sorry, 10:50. It's fine. Okay, thank you. If you have any questions, okay, that's fine. After this, we will see some MATLAB model that will be interesting for you, but you have to learn by yourself. I give you already uploaded the software, which is the model available in MATLAB readily. It is not my invention. Already everything is there, but it's our brain. We adapt to learn. Thank you. See you soon. Bye.